Okay, hello everybody. So in this module, we're going to look at the time response characteristics, and that is in chapter 6. So far we've been discussing different methods for representing continuous and discrete time systems. And now that we know how to represent these systems and get the transfer function, we can start studying and analyzing these systems. And we're going to start with the time response characteristics. Now, just to know where we are in the class, we're going to be looking at the steady state errors next. Then we're going to look at the stability. We're going to look at root locus. We're going to look at gain and phase margin. We're going to look at controller. And we're going to look at modern techniques in the control systems. Now, also, I want to emphasize, or I want to mention one thing. So we've been spending lots of time in the representation of these systems. Now, when we studied the control systems, for continuous time systems, we only spent a week on the representation of the system. We just used Laplace transform. We probably spent 1, 2, 3 lectures on modeling of the system, and then we moved on to the analysis of the system. In this course, we spent lots of time on the representation of the systems, and then we're going to move on now to analyzing the systems. Now, this is what you're going to keep in mind. Lots of the things that we're going to be discussing from now on are going to be built on what we learned in control systems in the previous class. So please, if you need to, you might have to go back and refresh on some of the topics. So for instance, root locus, we're going to present it with the assumption that we know how to plot the root locus. And therefore, unlike when we discussed it in the continuous control, we spend probably a few modules or a few lectures on it to introduce it. Here, we're going to just use the knowledge that we have of root locus. So that way, I mean, both courses will balance out. Here, we're spending more time on the representation because it's more complicated. But at the same time, lots of the concepts that we're going to be discussing later on are going to be based on concepts that we are familiar with. Okay. So before we start our time response analysis, let's just recap what we have done so far. So let's look at this system. If we have this feedback system, and what we want to do is we want to calculate the transfer function of this system, or also calculate the output of the system. Now, if I look at this system, we have R of S, which means it's a continuous time signal. We have C of S, it's a continuous time signal. And we have G of S, which is a continuous time system. Now, at the same time, we have a sampler here. So therefore, here we have the signal, the error signal, that is R minus C of S, is sampled and applied to the continuous time system. Now, keep in mind, when you see something like this, what is this system in reality would look like? This signal is sampled and then applied to a continuous time system. So immediately, we're going to know that this G of S must have a zero order hold in it. How do we know that? Because how do we sample this signal? So if I look at this system, how does this system look like? The physical system. I'm going to have a microcontroller. I'm going to have, let's say this system that we're trying to control is a motor. So this is my motor. I'm taking the position, for instance, of this motor, and I'm subtracting it from the signal that I want to apply. So I have a knob, or I have a potentiometer that I can set the position of the system. And I'm taking the signal, the difference between where I want the position to be and the current position, and I'm subtracting them from each other. So let's say I have an op-amp that subtracts the two signals together, R and subtract C, the output and the input, the output and the input. Now this signal, it says here, I'm taking it through an analog to digital converter. So I'm taking this signal to an analog to digital converter. So now this signal after it's sampled, it's inside this microcontroller or inside this computer. It's in a digital format. I cannot apply it to a continuous, to this motor. How do I apply it to this motor? I'm going to have to take it through a digital to analog converter and then apply it to this motor. And therefore, since I'm going to be using a digital to analog converter in order to be applying it to a continuous time system, this G of S must include the digital to analog converter, which is the zero order hold. Okay. So therefore, this G of S here contains the zero order hold and the transfer function of the system, and what we've been calling GP of S. Okay, so to get the transfer function, we know that C is equal to G multiplied by E star. E is equal to R minus C, and C is equal to G multiplied by E star from here. And therefore, if I take the star transform here, is going to equal E star is going to equal R star minus G star multiplied by E star. Since this G is multiplied by a starred function, when I take the star transform, each one of them is going to be starred. So therefore, I can write E star is equal to R star over 1 plus G star. If I move this to the other side, I'm going to get the E star to equal this R star over 1 plus G star. But C is equal to G multiplied by E star. So therefore C, I can multiply E star by G. I'm going to get C equal to G multiplied by R star over 1 plus G star. Now if I take the star transform, I'm going to get C star equal to G star multiplied by R star over 1 plus G star. Now that I have everything in the star transform, I can get the Z transform. I replace E to ST with Z. I'm going to get C of Z equal to G of Z multiplied by R of Z over 1 plus G of Z. So this is the first step. I got the transfer function between the input and the output. Now what is G of Z? I can calculate G of Z using the residue method. G of Z is equal to Z transform of 1 minus E to ST over S, this is from the zero order hold, multiplied by 4 over S plus 2, which is the transfer function GP of S. Now this, I can write it, take this numerator out, is going to equal to 1 minus Z to negative 1. This S, I'm going to add it to the transfer function. So I'm going to get 4 over S multiplied by S plus 2. Now taking the Z transform of this, I can, using the residue method, or I can use the tables in the appendix. If I expand 4 over S multiplied by S plus 2 is going to be 2 over S plus negative 2 over S plus 2. These are the residues, 2 and negative 2, and these are lambda 1 is 0, lambda 2 is negative 2, the poles of the transfer function. So therefore G of Z is going to equal 1 minus Z to negative 1, 2 divided by 1 minus Z to negative 1, E to 0, the lambda 1, plus negative 2 over 1 minus Z to negative 1, E to negative T multiplied by 2, where this negative 2 is coming from lambda 2. Okay. So therefore, if I simplify the expression, I'm going to get G of Z. Of course, we are given in the problem that T is equal to 0.1 second. So if I plug in T equal to 0.1 second and simplify this expression, and I know, some of the calculations here are cumbersome and it is very easy to make mistakes. Nevertheless, the more important is understanding the concept and being able to do the math. So if we do that, we're going to get G of Z. We're going to take this complicated expression, is going to simplify to this expression here, 0.365 over Z minus 0.8187. So now that we know G of Z, we can go back to T of Z, the transfer function, is going to equal to G of Z over 1 plus G of Z. If I plug in the G of Z that we simplified here, I'm gonna get the transfer function 0.3625 over z minus 0.4562. Now, if we are given the input, I want to calculate the output. If the input r of t is u of t, a unit step function, then r of s is equal to 1 over s, and the z transform of r of s 1 over s is z over z minus 1. And hopefully everybody, this sounds familiar or looks familiar, or with, with the exercises we've done, this makes sense. R of z is z over z minus 1. Then c of z is going to equal to t of z multiplied by r of z, which is equal to the transfer function multiplied by the input. Okay, so then we can calculate the inverse z transform if I want to calculate the output. And the output, we can do a partial fraction expansion and then use the formulas or use the expression, if we have it in this expression, to immediately calculate c of k. C of k is going to equal to 0.675. This is z over z minus 1, which is u of k. And this is negative 0.66567 z over z minus 0.465. This is going to give me 0.667 multiplied by this to the power of k. And this, what this tells me, if I were to look at samples, if I were to look at samples of this continuous time system output, every t second, these are the values that I'm going to get at that output. Okay, so this is what we've been doing in the last few modules, and hopefully this is now more familiar and makes sense to everybody. Now what we're going to do is we're going to start looking at the time response of the system and see what determines the response of the system and what factors will determine the shape of that response. Now before we do that, let's review the continuous time system response. So what we're going to do, we're going to review the continuous time and then we're going to move to the discrete time systems. So if I have a single input, single output linear time invariant system that is represented by state space representation that we have here, we have an input u of t and output y of t. Then if I applied an input u of t at time equal to 0, then the output y of t is going to be given by the expression that we have here, by this expression here. Y of t is going to equal to the C matrix e to a c multiplied by t multiplied by the initial condition x of 0. So we have initial conditions here, x of 0, plus cc integration from 0 to t e to a c t minus tau bc u of tau d tau. This is the response that is due to the input. So the output is made up of two components, one that is due to initial conditions and one that is due to the input. Now we discussed this at length in module 5. So if you're going to look at this expression, you can go back and look at module 5 and refresh on it. Now this is the expression in the time domain. In the frequency domain, y of s is equal to c multiplied by si minus a inverse multiplied by x of 0, the initial condition, plus cc si minus a inverse multiplied by b multiplied by u of s. Now this part of the expression, we called it the transfer function. Remember, the transfer function is the output over the input when the initial conditions are set to 0. So if I set this initial conditions to 0, then y of s over u of s is going to be h of s, which is given by c. Now I have a subscript c here because this is continuous. So all the a, b, c have a subscript of c in them. So there's a c here. Okay. So we notice here, when I look at the poles of y of s, I have poles that are coming from Si minus A and poles that are coming from Y of S. So the poles at the output in the expression of the output Y of S are going to have poles that are coming from the system Si minus A, the system that we're applying the input to, and some poles that are going to be coming from the input U of S. Now, if you recall, we defined the transient response of Y of t, and that is the response that is determined by all the poles of Y of S. So overall, all the poles work together to generate the transient response. We also have something that we call the natural response, and this is the response that is determined by the poles of the system, Si minus A inverse. Together, the transient response includes the natural response. Okay, so let's look at an example to illustrate all this. So suppose that we have a system and we applied an input U of t e to negative t multiplied by u0 of t, which is the unit step, and the system is given by x dot equal to negative 2x plus u of t. We have initial conditions that is 10, and y is just equal to x of t. We're going to find the overall response as well as the natural response of the system. So to do that, we know that A is negative 2, B is 1, C is 1, and D is 0. And using the expression that we just had in the previous slides, y of t is going to equal e to negative 2, which is the A, multiplied by t, multiplied by initial conditions. This is the 10 is the x of 0, plus the integration from 0 to t, e to negative 2, t minus tau, e to negative tau, d tau. This is the response that is due to initial condition. This is the response that is due to u of t. Now we can also write this y in the s domain. Y of s is going to equal to, if I take the, if I can take it directly from here, if I take the Laplace transform, it's going to be 10 over s plus 2. And this integration is going to be the multiplication of h of s multiplied by u of s. Remember, multiplication in the frequency domain is going to be convolution in the time domain. So this expression here is the convolution, and in the frequency domain is going to be the multiplication. So it's going to be the multiplication of h of s, the transfer function, multiplied by u of s. Okay, so therefore y of s is going to equal to these three terms. Now I can simplify, since these two have the same denominator, I can add them together. 10 minus 1 is going to give me the 9, and this is going to stay 1 over s plus 1. Now if I look at this y of s, I can take the inverse Laplace and get y of t equal to 9 e to negative 2t plus e to negative t. Now if I look at this expression, the expression, this overall expression is the transient response. This part of the transient response is the natural response. And this is coming from the poles of the plant, the s equal to negative 2. So part of the transient response is the natural response, and that is coming from the poles of the plant itself. Now there is another term here that is coming from the input. Okay. Now we can also get this y of t directly from the integration that we have, the formula that we have there. Y of t is equal 10 e to negative 2t plus e to negative 2t, integration from 0 to t, e to tau d tau. And if we integrate, we're going to get 10 e to negative 2t, e to negative 2t multiplied by e to t. Again, this is the convolution. and hopefully everybody is familiar with it. So if you do this integration, we're going to get 10 e to negative 2t plus e to negative t minus e to negative 2t. This is the response due to the initial conditions. This is the response that is due to u of t. When we add them together, we get 9 e to negative 2t plus e to negative t. Now this time constant here, e to negative 2t, is coming from the plant itself. This is coming from the input signal. Okay. So now what we want to look at is the relationship between the time response and the poles of y of s. And if you remember, when we studied the feedback control, we defined multiple metrics to characterize the response of the system. We defined the rise time, the time it requires the output to go from 10% to 90% of the final value and stay within that. We define, the time it requires to the output to go from 10% of the final value to 90% of the final value. And then we define the settling time, which is the smallest time where the output will reach and remain within a percentage of the final value. And in this case, the percentage is 5%. We choose it as 5%. And then we have the maximum overshoot. And if we have the maximum is greater, the maximum of the response is greater than the steady state value of the response, then we define the maximum overshoot as y max minus y steady state divided by y steady state multiplied by 100%. And we can also define a maximum undershoot if the minimum value of the output is less than, if the steady state value is greater than 0 and greater than y minimum. And let's look at the graph to illustrate all this. So if this is the response of the system in general, and it has an overshoot, then we can define the maximum undershoot, maximum overshoot, y max, y min. This is the settling time. This is the steady state value. This is 5% of that steady value plus minus. The time it reaches this narrow strip and stays within this strip, we define that as the settling time. The rise time is the time it goes from 10% of the steady state value to 90% of the steady state value. Not the maximum here. So we look at the steady state value. This is the steady state value here. And 10% and 90% of the steady state value. Okay. Now also in the linear control, we looked at the second order system, and we said the second order system is a very interesting system because it shows lots of the dynamics and lots of the different characteristics of the output. And in many cases, we might be able to take a higher order system and approximate that system with a second order system. So therefore, we spend lots of time studying the second order system. Again, why is it we studying the second order system? The first order system, if the system is a first order, the characteristics is straightforward, is an exponential signal. There isn't much dynamics that we can study. If it's a second order system, then we have more dynamics that we can look at the response of the system. And therefore, it makes that response more interesting. Now, if we have a higher order system, we can always try, if we can, to approximate that response with a second order system. Now, the second order system is, if you remember, the transfer function is omega n squared over s squared plus 2 zeta omega n multiplied by s plus omega n squared. And if I take the poles of this system, there are the roots of this characteristic equation. And these roots are going to be S1 equal to negative zeta omega n plus or minus omega n multiplied by square root of zeta squared minus 1. And we can write this as equal to negative zeta omega n plus or minus j omega n square root of 1 minus zeta squared. So I took a negative 1 here, and this becomes 1 minus zeta squared, and that will give me the j here. Now this we define it as omega d. And if I want this system to be stable, if zeta is greater than 0 and omega n is greater than 0, the system is going to be stable. How do I know that? Because for the system to be stable, the poles of the system have to be in the left half side. So this is, if this is my S-plane, I want these roots to be somewhere in the left half plane. For these roots to be left in the left half plane, negative zeta omega n must be in the left half plane. So therefore, I want zeta and omega n to be greater than 0. Since they're multiplied by a negative sign, the pole is going to be in the left half plane. Okay. Of course, we study all these characteristics that we're going to be studying next if the system is stable. If the system is unstable, then none of this will apply. Okay, so if you also recall, we looked at, when we studied this second order system, we looked at what happens when zeta is between 0 and 1. We call this system underdamped, and the response of the system is going to look like we have it marked here in red. It's going to have an overshoot, and then it's going to settle down. And in this case, we're going to have two roots that are going to have the poles of the system are going to have a real part, imaginary part. Now if zeta is equal to, if we keep increasing zeta, these poles are going to move closer to each other. Eventually they're going to be on top of each other. So I'm going to have two poles here when zeta is equal to 1, and in this case I'm going to have a response that is critically damped, which is this response here that I see in blue. And if I keep increasing zeta, these poles are gonna start moving this way, and therefore I'm gonna have two poles along the real axis. And in this case, I'm gonna have an overdamped response, which is the response that you see here in green. Now this is the expression for each one of these responses, and you can see how just by changing the zeta, the damping factor, we can get a different response of the system, going from a system with an overshoot all the way to a system that does not have an overshoot. Now one thing also just to keep in mind when we look at this response, if I look at the system that is underdamped, I realize this system is faster than that of the overdamped response. So depending on the application, I might be interested in having the response of the system go as fast as possible. So if I look at the response here versus the response here versus the response here, this response is much faster. So the underdamped response is going to be much faster at going to the steady state value compared to the overdamped response. Okay. So that was a quick review of the continuous time systems. And what we're going to be looking at next is the new topic, which is the discrete time characteristics. So if I look at a system that, similar to the example that we've done at the beginning of the class, I have T of Z. This is the transfer function between the input and the output. And I'm going to write the transfer function as multiplications of zeros over multiplications of poles. And we're going to see that the natural response is determined by the poles of y of z over r of z, which is the transfer function, which are the roots of the characteristic equation, which is the denominator in this transfer function. So if I take the roots of this transfer function, this is what's gonna determine the response of our system. Okay, so let's look at the transient response characteristics of the z-plane pole locations and look how does the location of the poles affect the time response characteristics of y of k. So if we have a system where r of z is known and we're going to calculate the response of the system y of z, we can express y of z as the multiplication of the transfer function multiplied by r of z, and then I'm going to expand this expression as k over z minus p1 all the way to kn multiplied by z over z minus pn plus all the terms that are going to come as a result of that input. So these poles are coming from the transfer function. There are poles that are going to come from the input itself r. I'm going to lump them together into y r of z. So these are the terms that originate in the poles of r of z. So all together will determine the output. I'm going to split them. The poles that are coming from the transfer function, I'm going to expand them. The poles that are coming from the input, I'm just going to lump them together. And the reason, because I'm trying to understand the behavior of the system irrespective of the input that I apply to it. Okay, so if I expanded y of z using these terms, I can write y of k, if I take the inverse z transform, as k multiplied by p1 to the k, all the way kn multiplied by pn to the k, and then plus the inverse of y r of z, which is going to give me y r of k. Now, similar to the continuous time system, this is the natural response, the response that's coming from the poles of the system itself, irrespective of the input. And this is the response that is due to that specific input that you're applying. Altogether, give me the transient response, the response of the system to that input. Okay. Now let's look at this expression here and see how would this response look like based on the value of these P1 to Pn. How do these P1 to Pn, P1 and to Pn are the location of the poles. So Z minus Pi, Z minus P1. So I have a pole at location P1, a pole at location P2, P3, all the way to Pn. This is the location of the poles of the system. How does that location affect the response or the shape of the response of the system? We can look at this table here. So if I have the pole location P1 equal at 1/2, so the pole is located. So remember, let me put it here. I have a unit circle in the z domain, so this is the z space, and now I have a pole here that is at 1/2. This is the unit circle. This is 1. This is 1. This is 1. This is, sorry, this is 1. This is -1. This is negative. This is J1. This is negative J1. Now I have a pole. If I have a pole of the system at 1/2, how does the response gonna look like? It's gonna be, according to this expression, P1 to the K. So here is gonna be 1/2 to the K. What is 1/2 to the K gonna look like? It's gonna look something like this. A decaying exponential signal. It's gonna be 1, 1/2, 1/4, 1/8, etc. What if the pole is at -1/2? How does the response gonna look like? It's gonna be -1/2 to the K, which is gonna be at 0 is gonna be 1/2. Sorry, at 0 is gonna be 1. At 1 is gonna be -1/2, positive 1/4, and so on. And so it's gonna be oscillating and decaying. What happens if I have the pole at 2, which means it's outside the unit circle? If it is at 2, it's going to be 2 to the K, It's going to be 1 at 0, at 1 is going to be a 2, at 2 is going to be at 2 is going to be a 4, at 3 is going to be an 8, and therefore is going to be a growing exponential signal. What happens if it is at negative 2? If it is at negative 2, at 0 is going to equal to a 1, at 2 is going to be negative 2, at 2 is going to equal to a 4, at 3 is going to equal to negative 8, and therefore is going to be oscillating and at the same time growing exponential signal. What happens if I have my pole at 1, right right on the unit circle? So if my pole is here at 1, what is the response going to be? 1 to the k, which is going to be a 1, 1, 1, 1. What happens if my pole is at negative 1? My response is going to be a 1, a negative 1, a 1, negative 1. So therefore it's going to be non-decaying, oscillating between 1 and negative 1. Okay, so what happens? So we looked at what happens if we have the roots along the real axis. Now what happens if I have an imaginary part? So if the poles are somewhere where they have an imaginary part. So for instance, a pole like 2 poles like this. Of course these come in conjugate because all the terms in the transfer function are going to be real. So therefore the poles are going to be in complex conjugates. So let's see what happens if I have 2 poles that are complex conjugates of each other, and they are complex, so they have real part and imaginary part. So let's say that we have P1 that is equal to 0.7 multiplied by square root of 2 over 2 plus j square root of 2 over 2, which I can write as 0.7 and j equal to pi over 4. And I have another root that is at 0.7 and negative j pi over 4. So if I go back to my unit circle, this could be my pole here, and this is the other pole, 1 at pi over 4, 1 at negative pi over 4, and the length of it is 0.7. How does the response of the system gonna look like? Well, we can just plug it in. Y of k is gonna equal to k1 multiplied by p1 to k plus k2 multiplied by p2 to k. And if we assume k1 is equal to k2, then I can write y of k equal to k1 multiplied by 0.7 to the k e to j pi over 4 to k. So I took the p1 and just took it to the power of k, plus e to negative j pi over 4 to the k. Now if I look at this, this is nothing other than a cosine. So I'm going to have a 2 multiplied by 0.7 to the k multiplied by k1 multiplied by cosine pi over 4 multiplied by k. And therefore, if I have a complex poles, they will give rise to an oscillating response. Now this oscillating response can be decaying or can be growing depending on this value here, 0.7. If it is less than 1, it's going to be oscillating, that is decaying. If it is greater than 1, it's going to be oscillating, that is growing. If it is less than 1, it means it's inside the unit circle, it's going to be decaying. If it is greater than 1, it means it's outside the unit circle, and it means it's going to be growing. Okay. Okay, so let's look at next the mapping between the S-plane and the Z-plane. So if I have a system that I have the Laplace transform y of s for it, how do these poles map into the Z domain? So if we have a signal y of t and we have y of s for that signal, we showed that the pole locations y of s plays the significant role in determining the time response. So therefore, if I have y of s equal to 1 over s minus s1, and the pole is at s1, depending on the value of s1, I can have a response that decays exponentially if s1 is less than 0. I can have a response that grows exponentially if s1 is greater than 0. I can have a response that remains constant if s1 is equal to 0. Now, what happens if I take this response and I sample it every t second? And therefore, I'm going to get that response of that system sampled every t second to give me y of k. Y of k is going to equal to, this is small letter s1 multiplied by k multiplied by t. So again, this is y of t e to s1 multiplied by t. I sampled every capital T second to get these samples y of k. Y of k is going to equal to e to s1 multiplied by k multiplied by t, which I can write as e to s1 multiplied by t to the power of k. Now, as in the continuous time case, the poles of y of z will determine the time response characteristics of y of k. So if I take the z transform of y of k, I'm going to get y of z. Y of z is going to equal to z over z minus e to s1 multiplied by t. A to k is going to be z over z minus a. Now, if I look at this y of z, it has a pole at z equal to e to s1 multiplied by t. Now, similar to the continuous time case, if s1 is less than 0, I'm going to have e to s1 multiplied by t to be less than 1, and therefore this is going to be a decaying exponential. If s1 is greater than 0, e to s1 multiplied by t is going to be greater than 1. This will be a growing exponential. If s1 is equal to 0, then this is going to give me a constant response. So we can see if I have a continuous time system, a continuous time signal, I sample that signal to get a discrete time signal. The characteristics of that response is going to be still determined by the S1, which is the pole that is in that signal. So this S1 that is in the continuous time signal is still determining the response of the discrete time signal that I sampled from that continuous time signal. Okay. So in this case, in this example that we've done, we considered what happens when we have one single pole. However, does this relationship hold when we have multiple poles instead of just a single one? And to answer that, we go back to how we get y of z. And if you recall, we get y of z from y of s star, and we replace z equal to st, and this is going to equal the summation of the residue associated with the pole lambda I of y of lambda multiplied by 1 minus e negative t s minus lambda I, and therefore we can write this as a summation of ci 1 over z 1 over 1 minus z to negative 1 e to t multiplied by lambda I, and we can multiply z over z. We can write this as summation of ci z over z minus e to t multiplied by lambda I. What does this tell me? This tells me that if lambda I is a pole in y of s, so lambda I is a pole of y of s, then z equal e to lambda I multiplied by t is a pole of y of z. So again, if lambda I is a pole for y of s. Then when I sample this and convert it to a discrete signal to get y of z, e to lambda I multiplied by t is going to be a pole in y of z. Okay. So therefore, let's look closer at this mapping z e to s multiplied by t, the mapping of that pole that we've seen here from the continuous time to the discrete time. S2, the pole goes from S1 to e to S1 multiplied by t. If SP is a pole of y of s, then z sub p is a pole of y of z, where zp is equal to e to sp multiplied by t. Agree? So this is what we showed so far. This is the pole of the discrete time signal if the continuous time signal has a pole at sp. Now what I want to do is I want to see how does this mapping in general works for any location in the S domain. So what I want to do is I want to look at how do poles map from the S domain to the Z domain. And to do that, I'm going to come to SP and say, okay, SP is a complex number. S, the pole, is going to have a real part that we usually call, or we call sigma, and an imaginary part that is W. So in the S domain, this is S space. If I have a pole here, I call this is negative sigma, and this is J omega. This is omega, this is the J axis, this is sigma. So therefore SP is equal to, this is sigma and this is J omega. SP is expressed as sigma plus J omega, and therefore ZP is going to equal e to sigma plus J omega multiplied by t. If I separate these, I can write this as e to sigma multiplied by t multiplied by e to j omega multiplied by t. Now this signal, the discrete time signal, is sampled, and we're sampling it. So we have the continuous time signal, we're sampling it every t seconds to get the discrete time signal. So 0, t, 2t, etc. So therefore our sampling time omega s is equal to 2 pi divided by t. Omega sampling is equal to 2 pi divided by t. And therefore this t is equal to 2 pi divided by omega s. And therefore I can come to this expression that I have here for Zp and say that Zp is equal e to sigma multiplied by t, e to j omega multiplied by t, but t is equal to 2 pi over omega s. So I just replace this t with this value of t, 2 pi over omega s. So now let's look at some properties of this mapping. This is how a pole in the S domain is mapped into the Z domain. And what we're going to do is we're just going to use this expression to look to get some properties of this mapping. Okay, so the first property, if I have lines of constant sigma in the S-plane, these lines are going to map into circles of radius e to sigma t in the Z-plane. What does that mean? Well, we have Zp equal e to sigma multiplied by t e to j 2 pi omega over omega s. Omega over omega s. Now I can write this as e to sigma t e to j 2 pi omega over omega s, I can write it as cosine and sine. E to j x is equal to cosine x plus j sine x. So therefore, if I take the magnitude of Zp, the magnitude, what is the magnitude? This is complex value. It's going to have real part, imaginary part. If I square the real part and the imaginary part, it will give me the magnitude. What is that magnitude? I'm going to take this real part, e to sigma cosine, square it, e to sigma sine, square it. If I do that, and then I'm going to take the square root of it, I'm going to get e to sigma t multiplied by square root of cosine plus sine squared. This is going to give me a 1, and therefore the magnitude of Zp is going to equal to e to sigma t. And to illustrate that, what this is, if I have poles that are along a constant sigma, so this line here in the S domain represent all the poles that have the same sigma 1. This line here represent all the poles in the S domain that have sigma 2. The real part of it is 2. I know that all the poles that are along this S1 are going to map into a circle that has a magnitude that is equal to e to sigma 1. And all the poles that are along sigma 2 are going to map into a circle that has a magnitude that is e to sigma 2. And you can see if I have poles along the j omega axis, sigma is equal to 0. If sigma is equal to 0, e to 0 multiplied by t is going to equal to a 1. So the real axis is going to map into, where is it going to map into? It's going to map into the unit circle. Does that make sense? Hopefully everybody is seeing that. How do I know this is a circle? Because it has a magnitude that is a constant. If I have a location, a loci that has a magnitude that's a constant, that will define a circle for me. All these poles that are along this circle have a magnitude that is equal. What is the magnitude here? The magnitude here, magnitude here, magnitude here. It's all equal to a 1. What is the magnitude if I am along this circle? The magnitude of the pole here is going to equal to e to sigma 2 multiplied by t. The magnitude is the same here, the magnitude. It has a real part, imaginary part, but if I take the magnitude, is going to equal to e to sigma 2 multiplied by t. And similarly, this inner circle here is going to have a magnitude that is e to sigma 1 multiplied by t. Now you can see if this sigma is negative. So if I have e to negative 2 multiplied by t, this is going to give me a circle that is inside the unit circle. If sigma is on the right half plane, sigma is greater than 0, is going to give me a circle that is outside the unit circle. Okay, so if there's a negative sign here, it's going to be less than 1. If it is positive, it's going to be greater than 1. Okay. Now you can see also that if the poles of the signal are in the left half plane and the signal is stable, they're all going to map inside the unit circle. If they are in the right half plane, they're going to map outside the unit circle. Okay. So the right half plane poles in the S domain map outside the unit circle. Left half plane poles in the S domain map inside the unit circle. Poles that are on the j omega axis map onto the unit circle. Okay. The second property, what happens if I have lines of constant W, constant omega in the S domain? These will map into radial rays that are drawn at an angle that is omega multiplied by t in the Z domain, in the Z plane. So what that means, if I come here to the S domain and plot a line, now all these poles along this line have different sigmas, but they all have the same j omega 1. This is j omega 1. Now this line is gonna map into a radial ray that makes an angle that is omega multiplied by t. And we can see it from here. Zp is equal e to sigma multiplied by t multiplied by e to j omega t. I can write this as magnitude and phase. The magnitude is going to equal to Zp, and the phase is going to equal to omega multiplied by t. So the angle here of this expression is omega multiplied by t. Since all these poles along this line have the same omega multiplied by t, they're all going to have the same angle. The magnitude is going to be determined by the sigma of each one of these poles. Okay. So let's consider the case where sigma is equal to 0, and let's map the poles. So let's consider this an example. Let's consider the case where sigma is equal to 0, and I have poles at 0, j omega s over 2, negative j omega s over 2, and I want to see how these poles will map into the Z plane. So just again, to remind everybody what we're doing. I have a signal here, let's call it y of s. These are the poles of y of s. I sampled this signal, I got y of z. I want to see how are the poles in y of s gonna map into the poles of y of z. Okay, so if I have these three poles, Zp1, Zp2, Zp3, the phase of Zp1 is going to equal omega s over 2 multiplied by t, which is going to equal to 2 pi over t multiplied by 2 pi over t is omega s multiplied by 1/2 multiplied by t, which is going to give me a pi. If Zp is 0, then the phase is 0. Zp3 is negative omega s over 2 multiplied by t is going to give me negative pi instead of a pi. So therefore, the DC when s is equal to 0, when I'm at the origin, is going to map to z equal to a 1, and when s1, when I am at omega s over 2, is going to map into pi, and when I am at negative j omega s over 2, it's also gonna map into a negative pi. So 0 is gonna map to z equal to a 1, zp2, zp1 and zp3 are gonna map into the pi and negative pi. Okay. Now what happens if I map the region below? So what I want to do, I'm going to come to the S-plane, I'm going to take a line, or I'm going to start at the origin, I'm going to go along the j omega axis from 1 to 2 to 3, then go through a line that is parallel to the real axis all the way to infinity. And then I'm going to come and from infinity all the way to 6, and then go along the j omega axis back to the original. and I'm going to choose these points here as j omega s over 4. This is j omega s over 2. This is negative j omega s over 4, negative j omega s over 2. So I want to see how does this line or this line map into the z-plane, or these lines. So if I look here, we know that the origin is going to map into 1 here. We showed it from just before. Omega s over 3, j omega s over 2, this point here, is going to map into 3. We just showed it before. Negative j omega s over 2 is going to map into 6. We also, I'm exaggerating this dotted line. This should be very close to the origin, but just to illustrate where it is. So both of these 3 and 6 are going to map into the negative pi. J omega s over 4 is going to map to pi over 2, which is the point here at 2. Negative j omega s over 4 is going to map into negative pi over 2. And this strip here from 3 to 4, at 4, remember this sigma is going to equal to negative infinity. And therefore is going to be the magnitude of it, e to negative infinity, is going to be very, very small. So it's going to be at the origin. So going from 3 to 4, I'm going to start mapping along this dotted line all the way to the origin. And the same thing applies from 5 to 6. When I'm at 5, sigma is equal to negative infinity, and therefore the magnitude is going to be almost 0. And as I get closer to the origin, I'm going to move from 5 all the way to 6 here. So again, z equal e to sigma t multiplied e to j omega t. As sigma goes to infinity along 3 to 4, the phase is equal to a pi, but the magnitude of zeta goes from 1 to a 0 because sigma is a negative value. So all these sigmas, so again, if I am at this point here, this sigma is a negative value. So e to a negative value that is very, very large is going to be very small. The farther I am from the origin, the larger that negative value and the smaller e to sigma multiplied by t. And that's why at the infinity, I'm going to be at the origin. Okay. So again, the mapping will have a magnitude that is e to sigma t and a phase e to j omega t. E to j omega t, if I am along 3 to 4, omega is constant. So I'm going to be along the same angle here. The magnitude is determined by where I am along the real axis. Okay. I hope this is clear. Okay. Now what happens if a pole in the S-plane has a frequency that is greater than omega s over 2? So coming here, what happens if the signal has a pole that is higher than omega s over 2? And that is the third property, which is poles in the S-plane whose frequency differ in integral multiples of the sampling frequency. Omega s 2 pi over 2 are mapped into the same locations in the z-plane. So any poles that differ by omega s over 2 are going to be mapped back to the same location in the z-plane. So again, if I come back here, if I have any pole here at this location, if I add omega s over 2 to it, this location, both of these are going to map into the same location in the z-plane. And to show that, zp is equal e to sigma t multiplied by e to j omega t, and therefore I can write this, I can multiply it by a 1. This is equal e to sigma t multiplied by e to j omega t, and the 1 is nothing other than e to j 2 pi multiplied by n. This is 1. So therefore I can write this as e to sigma t multiplied by e to j omega t, and I can write this multiply by t and divide by t. I'm going to get e to j 2 pi over t multiplied by tn, but e to 2 pi over t is omega s, and therefore I can write this as e to sigma t e to j omega t plus n multiplied by omega s, and therefore this e to sigma t e to j t omega plus n omega s is gonna equal to e to sigma t multiplied by e to j omega t. Make sense? So to see this here, if I have a pole at this location, S2 is at negative sigma, or at sigma plus j omega 1. If I take another pole that is at sigma plus j omega 1 plus omega s. So these differ by omega s. The difference between these together, omega s. The difference between them, this distance is omega s. Both of these are gonna map into the same location, z1. Similarly, if I take S3, S4, the difference between the imaginary part, the difference between them is omega s. Both of them are gonna map into z2. And the same thing, if I were to add another pole at this location here, and call this S, let's call it, okay, 1, 2, 3, 4, let's call this 5, and this is at negative j omega 1 plus 2 omega s. The same thing is going to map into z2. Now, just to give you more intuition why that is the case, remember when we are sampling, omega s over 2 is the Nyquist frequency. So if the signal that we are sampling have frequencies that are higher than Nyquist, these frequencies are gonna flip and appear at lower frequencies. Remember when we done the, or you might remember, when we've done the sampling and we did the ruler to get the frequencies when we do the sampling, we have omega s over 2, omega s, and so on and so forth. So if I have any frequency that is greater than omega s over 2, when I collapse this ruler, this frequency that is greater than omega s over 2 is going to show up back again here at frequency that is less than omega s over 2. Okay. We've seen this in signals and systems. So, I mean, if you feel like, oh, I might have seen it, I don't remember when, you can go back to the signals and systems notes and look at when we'll discuss the Carpenter's rule, how the frequencies that are greater than omega s over 2 will show up after we sample them. Okay, so let's end up with an example to illustrate everything we've done. So let's consider a system G of S that is a second order system, and this system has poles at S12, zeta omega n plus minus j omega n square root of 1 minus z squared. Now we know the equivalent z-plane poles are going to be e to s multiplied by t with s equal to s1 and s2, and this is going to equal e to negative zeta omega nt, and the angle is going to be omega nt square root of 1 minus zeta squared. So again, if I plug in S1, S2 here, is going to give me a magnitude and is going to give me a phase or an angle that is omega n multiplied by t square root of 1 minus z squared. I can write it in polar form, magnitude and a phase. R is going to equal e to zeta omega n multiplied by t, and omega n t square root of 1 minus zeta squared is going to equal to theta. And therefore from here I can take the natural log of both sides. It's going to give me zeta omega n multiplied by t is equal to negative natural log of r. And if I take the ratio of 1 and 2, if I divide them by each other, I'm going to get z. If I divide z omega nt divided by omega nt square root of 1 minus zeta squared, I'm going to get z over square root of 1 minus z squared equal to negative natural log of r divided by theta. And therefore I can solve for zeta from here. And zeta, if I solve this equation for zeta, if I multiply and square and then just try to lump the terms together so I get zeta, I'm going to get zeta equal to negative natural log of r divided by natural log of r squared plus theta squared. Okay. And also, if I take equation 1 here, zeta omega n multiplied by t is equal to negative natural log of r, and therefore omega n is equal to the negative natural log of r divided by t multiplied by zeta. And I can substitute for zeta from here, and I will get omega n equal to 1 over t square root of the natural log plus theta squared. Now if I look at the time constant associated with the poles is gonna equal to 1 over zeta omega n, and therefore I can express that using the zeta and the omega n as negative t divided by the natural log of r. So if I use the expression that I got for zeta here and the expression I got for omega n from here, and I plug them, I'm gonna get the time constant associated with a pole as equal to negative t over the natural log of r. And therefore we can write r is equal to negative exponential r is equal to exponential of negative t over tau. Okay, so again this is the poles are located at zeta omega n. 1 over zeta omega n is the time constant associated with it. So therefore if I use that knowledge to apply it to this example, so if I have the system that is given by this feedback loop, and if I were to calculate g of z, So similar to the example that we've done at the beginning of the class, I'm going to calculate g of z. So g of z, 1 minus z negative 1, z of 1 over s squared multiplied by s plus 1. Now to calculate this, I'm not going to use the residue because I have multiple poles at 0. And therefore, what I'm going to do, I'm going to just use the tables at the appendix at the book. The appendix give me a over s squared multiplied by s plus a. It gives me the expression for the z transform, and therefore if I plug it in, I'm gonna get this expression here. If I plug in the values, I'm gonna get g of z. So this is g of z from g of s here, and therefore I can calculate the transfer function t of z, g of z over 1 plus g of z. This gives me the transfer function of the closed loop system. Now if I look at the poles here, z1, z2 is going to equal to, if I take the roots of this equation, 0.5 plus minus j 0.618, which is equal to 0.795, and the angle is 51, which is 0.695, and the angle is plus minus 0.89 in radians. And therefore I can calculate zeta. Now this the notation is gonna look confusing because I have z and this is zeta, so please don't confuse them together. This is zeta of the second order system. Zeta, using the expression that we just derived here, as the expression for zeta, using this expression here, if I apply it, zeta is going to equal negative natural log of the magnitude over natural log of the magnitude squared plus the phase squared, which is going to equal to 0.25. Omega n is going to equal to, again, from this expression, from this equation here, is going to equal the natural log, and t, this is t, is equal to a 1. T is equal to a 1. So 1 over 1, this one is t equal to a 1. Natural log 0.795 plus 0.89 squared underneath the square root is going to give me 0.919, and therefore tau is going to equal to, according to here, negative t over natural log of r, which is negative 1 over natural log of 0.795, which is 4.3 seconds. Now this example is going to help you with the homework because it's going to be using some similar expressions to the ones we had in this example. Okay, this is the end of this module. I realize it's also lots of hopefully it's not new concepts, it's just concepts that we're semi-familiar with from control class, but now we're applying it to a discrete system. We're going to be continuing next module. We're going to be calculating the expressions for the steady state errors. Thank you, everybody.